In this lesson, we're going to introduce inverses of matrices and matrix equations. So first we're going to define what's called the identity matrix. And that's identified by a capital I with an N, I sub n. So we have a single number, n is the, can name the size of the matrix, because the identity matrix is the n by n, so it's called a square matrix. It has the same number of rows as columns. It's the n by n matrix for which each leading entry is a 1. So remember what leading entry is. Each leading entry is a 1 and every other entries are 0. So here's some examples of identity matrices. Here we have a 2 by 2. So I sub 2 just means 2 rows, 2 columns. There's our 1. I sub 3, here's our 1s. I sub 4, there's our 1. So that's what the identity matrices look like. And they behave like the number 1. So a lot of rules that we use for regular numbers we can use for matrices. For example, if I have a matrix A and I multiply it by its corresponding identity matrix, I'm going to get matrix A back again. So here's an example of that, or we'll do an example of that next. Alright, here we have an identity matrix and it's 2 by 2. And we're going to multiply it next to a 2 by 3. So our answer is going to be a 2 by 3. So that means I'm going to have 6 calculations. I'll put them over here. And the first one is going to be the first row, first column. So that's going to be 1 times 3. 1 times 3 plus 0 times negative 1. So we're going to get a 3. The second one is going to be first row, second column, 1 times 5 plus 0 times 2. So what you can see is the 1 is just repeating everything in that row, and the 0 is negating everything in the second row. So you end up with 3, 5, 6. If you do the same thing in the second row, that means I'm going to do the second row, first column, and what this 0 is going to do is going to take out everything, take out all the first numbers, and the 1 is going to leave the second numbers. So in the end, you end up with the same values that you started with. And as long as the columns line up with the rows of the original, you could multiply either the front or the back with the inverse, or with the identity matrix. So that ties into the next thing we're going to talk about, which is called the inverse of a matrix. And again, a lot of matrices, matrix operations, behave like regular numbers. So here's a definition. We're going to let A be a square. We call this a square matrix when we have the same number of rows as columns. So A is a square n by n matrix. Then if there exists an n by n matrix, and we're going to call this A to the negative first, with this property, when I multiply A by this A to the negative first, I get the identity matrix back out again. Just like if you were multiplying a variable times its inverse, you would get the number 1. It's the same thing with matrices. Then if that happens, we can say that this guy, A to the negative first, is the inverse of A. Now A has to be a square matrix for it to even have an inverse, but not every square matrix has one. So here's an example. Let's say I have matrix A is 2, 2, 5, 4. And its inverse is negative 2, 1, 2.5, negative 1. So I have A, and I'm saying that this other matrix is its inverse. Then this has to be true. When I multiply A by A to the negative 1, I should get an identity matrix back out again. So let's see. A is, again, we'll line them up, 2, 2, 5, 4. And I'm multiplying that by negative 2, 1, 2.5, negative 1, and let's see what we get. It's 2 by 2 and a 2 by 2, so I'm going to get a 2 by 2 back out again. 2 times negative 2 plus 2 times 2.5. That's my first term. Well, that's going to be negative 4 plus 5 is going to give me a 1. So that one works. And then 2 times 1 is 2. 2 times negative 1 is negative 2, so this guy's going to be 0. Now let's try the next row. 5 times negative 2 is negative 10. 4 times 2.5 is positive negative 10 and positive 10, so that should be 0. And then finally 5 times 1 is 5. 4 times negative 1 is negative 4, so you get 1 back again. So this is what happens when you multiply a matrix by its inverse. You get the identity matrix back again. You're going to need to memorize the formula for finding the inverse of a 2 by 2. Anything bigger than a 2 by 2, and you're going to use your graphing calculator. But let's say, so here's the formula for it. Let's say matrix A has elements A, B, C, D. These are the entries for matrix A. Then here's how you find its inverse. A to the negative 1 is this formula. It's a constant term in front. You're going to multiply that by 1 over this product, A, D, minus B, C. And you're going to multiply that into this matrix. And here's what you do. You switch A and D. And you don't switch C and B, but you negate them. So there's a little pattern to this that you can remember. This is the formula for the inverse of a 2 by 2. That's what you have to memorize. So here's an example. We're going to let A be 4, 5, 2, 3. I want to find the inverse. And then if you multiply them together, you'll see that you will get the identity matrix back again. So to find the inverse, A, negative 1, it's going to be 1 over 4 times 3 minus 5 times 2. And then on the inside, you're going to switch the 3 and the 4, and you're just going to negate the 5 and the 2. So this ends up being 1/2 times all that, which gives me A to the negative first. You got to multiply the 1/2 through. 1.5, negative 2.5, negative 1, and 2. So if you were to multiply that by A, and again, it doesn't matter which way you multiply these because they're square, you're going to see that you're going to get the identity matrix back. You're going to end up with 1, 0, 0, 1 again. So we use that. Now we're going to talk about inverses of bigger matrices, matrices that are bigger than 2 by 2. Alright, to calculate the matrix of something bigger than a 2 by 2, the first thing you're going to do is you're going to enter the matrix, and it has to be square, otherwise you won't have any inverse. So you got to have the same number of rows as columns, so it must be n by n. Okay, and then you're going to call up that matrix to the main screen, whatever you called it. And then all you have to do is use the reciprocal button. Use the button that's x to the negative first. That's all you got to do. And then if there's a bunch of decimals, you can write in fraction format, enter, enter, and you'll see it in fractions. So that's all you have to do to find the inverse. If you have your graphing calculator with you, you can try this problem. Otherwise, we're going to do this in class. Alright, so we can use inverses to solve a system of equations. This is another way that we use matrices to solve linear systems of equations. So here we go. If A is a square matrix, a square n by n, and that it does have an inverse, because not all of them do, but let's say this one does, and then we're going to call X a variable matrix, and B is going to be a solution matrix. I don't have enough room here. Both with n rows, then we can write a matrix equation. And it looks like this. The matrix A, he's the coefficient matrix. That's all the coefficients on the left-hand side of your equation. X has the variables, so it's a one column of x, y, z. And then B has all the solutions in it. If that's my matrix equation, then we can solve it by multiplying A to the negative first by B. It has to be in this order. the inverse has to go first, and then it would work. Okay, so we will finish with this last example here and then do more in class. Let me show you how this works. Here's my system of equations. I'm going to break this up into three matrices. I'm going to write my coefficient matrix, and he's going to be 1, -2, -4, 2, -3, so it's all the coefficients on the left-hand side, -3, 6, and 15. There's my coefficient matrix. To that I'm going to multiply my variable matrix, x, y, and z. And that's going to be equal to my solution matrix, 7, 5, 0. So what you would do is you would enter two matrices in your calculator. You would enter your coefficient matrix into A and your solution matrix into B. And then what you would do is call up matrix A, invert it, and then multiply that. Call up matrix B and multiply them together. What you will get out is your answers, -11, -23, and 7 in this case. What that tells me is that x is -11, y is -23, and z is 7. So that's another way to solve a system of equations. And this way is used quite a bit in engineering, at least when I was back in school. We'll be working more of these examples in class.